Hello everyone. Today we'll discuss very important portion of higher engineering mathematics, that is a linear differential equation. Already you know the differential equation has a wide application in the field of medical science, in the field of engineering, physics, chemistry, biology, economics, and many more fields. These are the outlines of today's discussion. What are the linear differential equation with constant coefficients? What is homogeneous and non-homogeneous differential equation? And what are the methods, procedure to solve and the related problems? First of all, what is linear differential equation? Before linear differential equation, the linear differential equation means it is a differential equation where the dependent variable and its derivative not multiplied together. For example, I take double derivative d square y by dx square minus dy by dx plus y is equal to 0. Another one, fourth derivative d4y by dx 4 plus y is equal to 0. These are linear differential equation. Why? Because in each derivative term, it is multiplied with the only constants, not with the dependent variable. Dependent variable is y and particularly independent variable is x. Y never multiply with the derivative, either first derivative, second derivative or third derivative. Whereas the second example, I take y dy by dx plus 5y is equal to x. It is non-linear since in the first term y and its corresponding derivative dy by dx are multiplied together. Our question is how to solve these linear differential equation with constant coefficients, particular two examples. And another one is what is homogeneous and non-homogeneous of a linear differential equation. When the right side is 0, it is homogeneous, and when the right side one is non-zero, means it is a function of x, maybe function of both x and y or function of y, it is a non-homogeneous. The most general form of a linear LD means a linear differential equation of order n of the form is a0 into dny by dxn plus a1 into dn minus 1 by dxn minus 1 and continue up to any is equal to fx. And particularly I take here a0 not equal to 0, because if a0 means constants is equal to 0, it will not be order n differential equation. And where these a0, a1, an are all constants, and fx means a right side term is a function of x only of a linear differential equation. And we denote a letter capital alphabet D for differential operator, so that the above differential equation can be written as a0 dn plus a1 dn minus 1 up to an into y is equal to fx. That is, I denote here capital D for d by dx. This is the notation here. That is dy by dx, it will be d of y. Suppose d2y by dx square, it will be d square of y, and so on. Any derivative with the second order, third order or nth order, it will be dn plus dn minus 1 up to an minus 1 into d is equal to fx. This is the notation of a differential equation. Now come to how to write the differential equation in a common format. Another case, when the already told in the previous slide, when the right side of fx1 is not equal to 0, it is a homogeneous, and when this is not equal to 0, it is a homogeneous, and not equal to 0, it is non-homogeneous. And how to solve the procedure is, we first take the differential equation in the form of f dy is equal to 0. f dy means it is a function of d In the last slide, the a0 plus a1d plus up to and so on, this is function of d is equal to fx, and this can be simplified in the form of y is equal to fx, or y is equal to in the form of u plus v, where u is complete solution of the differential, means this is auxiliary equation f dy is equal to 0, called complementary function or shortcut CF, and V is the particular solution, or in the symbolically Pi. For example, the linear differential equation, I take linear differential equation second order, d2y by dx square minus 5 dy by dx plus 6 0 is clearly homogeneous because right side 0, but the second one is 3 sin x because it is not equal to 0, or it is a function of x, clearly it is non-homogeneous. This is the method of solve how to simplify or get solution of a linear differential equation. These are the steps. Step 1, suppose write the given differential equation in the form of f dy is equal to 0. F dy means function of it is d. In the last slide, function of d is equal to 0. This is function of d. Second one, next we write the auxiliary equation. Auxiliary equation means the only FD part when equal to 0. This is called auxiliary equation. And solve it. Solve it, see, this is algebraic equation we will consider in the next slide. So depending upon the nature of roots, or based on the nature of roots. Nature of roots means these are maybe non-repeated real numbers, repeated real numbers, maybe some imaginary numbers or complex number like alpha plus I beta form or 3 plus 4i form. In this way, based on the nature of roots of the auxiliary equation, write the complementary function. These are the procedures how to solve a linear differential equation with constant coefficients and get the required solution of the given homogeneous. Particularly today we will discuss the only homogeneous, means the right side of the differential equation is 0. There are 4 steps. These are important now. When all roots of the auxiliary equation are real and different or distinct, that means the roots are in the form of suppose m1, m2, m3 and so on, etc. Then the complete solution means this is the complementary function. It will be form of c1 m1x plus a c2 m2x plus a c3 m3x and so on. And how it is? Suppose I write a differential equation dy by dx plus suppose m1 y is equal to 0. Clearly this is a linear differential equation and its corresponding symbolic form is d minus m1 of whole y is equal to 0. So our question is, what is the answer of our solution of this differential equation? Clearly this is a form of general form of a linear differential equation. In the last class we already discussed. This is nothing but dy by dx plus py is equal to q, where p and q both are function of x. Clear? Both are function of x. So how to solve it? First we find the integrating factor if, which is nothing but integration of e to the power p, and here e to the power p is nothing but p is what here? P if I consider p is here m1. That means see integration of minus m1 x dx, or is nothing but e to the power minus m1 x. This is the if value, and the complete solution is y into if is equal to q into if, only right side part integration. So after simplification it will be y into e to the power minus m1x, but what is q here? Q is the right side one, q is 0 here. So integration of 0, but integration of 0 is a constant because constant derivative is 0. So it is nothing but, suppose it is single term, I take c1. So y is equal to c1 e to the power mx, c1 by e to the power minus m1x, or it will be goes to numerator will be positive. So I write here the complete solution, since there are different terms will come in the next slide we will discuss. c1 e to the power m1x, c2 e to the power mx, and so on addition. When that means, see, when the roots are auxiliary equation are real and different. Similarly, when the roots are real and equal, suppose here m1 and m2, m1 is equal to m2, two roots are equal. So in this case, after simplification like the previous one, the complete solution will be c1 plus c2x whole bracket into e to the power m1x. We can write also here e to the power m2x, and other for other solution or other roots, these are the others notations. Similarly, these are the case of a real, equal, and real and distinct. Similarly, other two cases may be, suppose roots are complex roots. Complex roots means in negative number square root. Already know, suppose the -1 is a root over denoted by symbol capital Y, or -4 root over denoted by, because 4 root over plus minus 2, and negative number we denote by small I. Then after simplification, the final solution is, or complementary function is, when the roots are complex, means it distinct complex, alpha plus I beta, other one is alpha minus I beta, where alpha is the real part, beta is the imaginary part. So solution is e to the power alpha x plus, into c1 cos beta x plus c2 sin beta x, and other roots what accordingly write the solution. Similarly, when the roots are repeated complex, that means m1 m2 is equal to alpha plus beta, or m3 m4 other two roots alpha minus r beta, then its the corresponding solution is, or complementary function is, e to the power alpha x into whole into c1 plus c2x whole into cos beta x, c3 plus c4x into sin beta x. And let us consider these facts in taking an example. Suppose I want to solve d2y by dx square minus 5 dy by dx plus 6y is equal to 0, which is a homogeneous linear differential equation. Why? Because the right side is 0. Also dependent variable and derivative not multiplied together. First, what are the procedure? We write its corresponding symbolic form. The symbolic form is what? Because d2y by dx square stands for d square y, dy by dx stands for capital D. So its corresponding form is d square y minus 5 dy plus 6 is equal to 0. Taking y common to RHS, d square minus 5d plus 6 is equal to 0. So this is the symbolic form. Which one? FD. FD is equal to 0, and which is the auxiliary equation. So auxiliary equation here is d square minus 5d plus 6 is equal to 0. Clearly this is a quadratic equation. From lower class we know how to simplify either by factorization method or by another minus b plus minus b square minus 4s by 2a. This is another method. Because this is factorized, d square minus 3d minus 2d plus 6 is equal to 0. And in higher class we don't write every steps, we simplify with skipping some statements. So it is now d minus 2 into d minus 3 is equal to 0. And taking each one 0, d is equal to 2 or d is equal to 3. That means this is real and distinct. Distinct means 2 and 3 two separate number, and 2, 3 both are real numbers. And this one comes under case 1 in the previous slide, whose solution is, hence CF complementary function is c1 e to the power m1x. m1 means 2 stands for here, 2 is here m1 and 3 here is m2. So that c1 e to the power 2x means m1x plus c2 e to the power 3x. So the complete solution is y is nothing but y or sometimes written yc complementary function c1 e to the power 2x plus c2 e to the power 3x, which is the required solution of the given differential equation. Clear? Similarly, we take another example. Suppose d3y by dx cube, which is the third derivative, minus d2y by dx square plus 3dy by dx minus y is equal to 0. Exactly same process. First we write the symbolic form. Symbolic form is its symbolic form is the third derivative dq, second one d square, third one d. So dqy minus 3dy square plus 3dy minus y is equal to 0. And taking y right side common within bracket, dq minus 3d square plus 3d minus 1 and whole into y is equal to 0. And clearly the function of d, that means d minus 1 whole cube is equal to 0, because already you know a minus b whole cube formula like this: a cube minus 3a square b plus 3ab square and minus of b cube. So using this fact, d minus whole cube is equal to 0. Since it is whole cube here, we multiplied with 3 times. That means d minus whole cube is nothing but d minus 1 into d minus 1 and another d minus 1 is equal to 0. So since by algebra method each one multiplied together 0, that means each term must be 0, so that d minus 1 is equal to 0, this one also 0, this one also 0. So from this fact we take a d is equal to 1, 1 and 1. Now see here 3 roots are equal and all are real. So here I write d is equal to 1, 1, 1, repeated real roots. So its corresponding formula is method 2, case 2. So complementary function is c1 plus c2x c3x square into whole e to the power mx or m1x or m2x, but m is here 1, 1x. So corresponding solution is, this is the y is equal to c1 plus c2x plus c3x square whole into e to the power x. Clear? So the case 1, case 2. Now to come to another example. Suppose under case 3, maybe it is real or complex or a combined form of real or complex. Let us see. So solve the differential equation dqy by dx cube plus y is equal to 0. Clearly the using the previous knowledge, the symbolic form is dqy plus y is equal to 0. Clear? So taking y right side, dq y plus 1, this is equal to 0, and the corresponding auxiliary equation is dq plus 1 is equal to 0. So now see, if I simplify using our previous algebra method, dq plus 1 is equal to 0 and dq is equal to minus 1, but this one never simplified. So we use here formula dq plus 1 means 1 cube. So now it is under the algebra rule a cube plus b cube formula, whose factorization is a plus b into a square minus ab plus b square. And here a is d, b is 1. So d plus 1 plus d square minus a d into 1 d itself plus 1 is equal to 0. And again taking each one is equal to 0. This is 0 and this is 0. So d here is minus 1 and d from simplification using the formula minus b plus minus b square minus of 4ac divided by 2a, because this is not factorized. Those quadratic equation cannot be factorized, we take the help of this one. So b here is minus 1, d coefficient minus 1, d square coefficient 1, and c here is compared to this one, c is 1. So minus of minus 1, it is now 1 plus minus 1 minus 4 square root divided by 2, and clearly 1 minus 4 is minus 3 and minus 3 square root is nothing but root 3 into I, where I stands for minus 1 square root. So taking the separate division, half plus minus root 3 by 2i. Now see, this is not real half is compared to our previous case 3 alpha plus I beta. One is alpha plus beta I beta and other is alpha minus I beta, where alpha is half, beta is root 3 by 2, and its corresponding solution is e to the power alpha x means e to the power alpha into x means half into x by 2 plus c2 plus cos 3 by 2 root 3x plus c3 sin root 3x by 2. But for this real, we take the help of case 1, c1 e to the power minus x e to the power x by 2 means alpha x here, and these are the answer. So the final solution is y is equal to c1 into e to the power minus x plus e to the power x by 2 cos root 3 by 2x plus c3 sin root 3 by 2x, which is the required solution. Suppose I consider another example taking the help of these facts. Suppose write dq y by dx cube minus y is equal to 0. Question is supposed solve. Clearly the corresponding the symbolic form is dqy minus y is equal to 0, and clearly auxiliary equation is taking y common, dq minus 1 whole of y is equal to 0. Auxiliary equation is dq minus 1 is equal to 0, and this again comes under aq minus bq formula, whose answer is a minus b into a square plus ab means d plus 1 is equal to 0. So taking each one 0, d is equal to 1, or d here is minus b, here b is 1 minus half plus minus 1 minus 4ac, 4 1 into 1 whole square root divided by 2 into 1, which is nothing but minus 1 plus minus 1 minus 4 itself, which is root 3 I divided by 2, or is nothing but minus half plus minus root 3 by 2i, which is the form of again alpha plus minus I beta, where alpha is minus half, beta is again root 3 by 2i. Similarly, using the case 3, the complete solution or final solution is e to the power alpha x, because d here is 1, another is d here, this is complex, this is one real x. So e to the power alpha x into c1 cos beta x plus c2 sin beta x, and for real one I write here c3 into 1x, because 1 is here m compared to previous. So final answer is e to the power alpha here is what? Alpha is minus half. So it is now minus x by 2 c1 cos of beta x, beta here is root 3 by 2x plus c2 sin root 3 by 2x and plus c3 e to the power x. So clearly this is the final answer. Similarly, we consider several examples taking same idea. So this much today. Next class we will discuss more about the linear equation and particularly non-homogeneous. Thank you all.